Assalamualaikum and hi everyone. My name is Khairunisa Shafa binti Kamaruniza with matrix number S70837. In this video, my group and I would like to talk about our study of self-powered smart kitchen kettle or smart shower temperature display utilizing thermoelectric generation. Before we start, this is my group member.
Assalamualaikum warahmatullahi wabarakatuh. Today we are presenting our design for a hybrid self-power wireless power transfer system utilizing thermoelectric energy harvesting from waste heat. My name is Muhammad Ruzaidi Ikhwan Razak S71AA7 and I am joined by my team members. Let's begin by addressing the fundamental problem that motivates this project. Conventional wireless power transfer system like those used to charge smartphone rely entirely stable electrical grid. This is significant limitation because it prevents WPT from being deployed in remote, off-grid or energy scarce environments. At the same time, a massive amount of low-grade waste heat is constantly being dissipated into the environment from everyday domestic appliances, representing a completely waste energy source. Our project bridges these two concepts. We are proposing a hybrid self-power availability architecture that completely eliminates grid dependency. Instead of plugging into a wall outlet, our system harvests ambient thermal energy from the base of the domestic heater after boiling. This waste heat converted into electrical energy using a thermoelectric generator, which drives resonant inductive coupling link to transfer power wirelessly across an air gap. Now let's talk about the engineer's challenges. There are two major hurdles we had to overcome. First, TEG produced a very low voltage, so we needed advanced power management IC with maximum power point tracking to extract every possible milliwatt. Second, inductive WPT is notoriously inefficient over distance. Our solution to that is precise resonant tuning and using high quality least wire coils to minimize resistive loss. The objective of our project to mathematically validate this entire concept and prove the complex power budget analysis the system can reliably deliver a regulated output to a low power consumer device. If successfully, this design offers a sustainable energy recycling solution that contributes directly to green energy initiative and opens the door for totally wireless self-sustaining electronic in the future.
The core of our system is the Seebeck effect discovered in 1821. It states that when you create a temperature difference across a conducting or semiconducting material, an electrical voltage is produced. In our thermoelectric generator, one side is heated by a kettle base while the other side is kept cold by a heat sink. Charge carries either electrons or holes, diffused from hot side to the cold side, creating electrical potential. The open circuit voltage is given by V open equal to alpha times delta T, where alpha is the Seebeck coefficient and delta T is temperature difference. For bismuth telluride, the material we use, the Seebeck coefficient is about 200 microvolt per Kelvin. So at a 75-degree temperature difference, we got around 15 millivolts. The material's efficiency is determined by its figure of merit, reduced heat loss, and increased power output. Bismuth telluride is ideal for our application because it performs best between 16 degrees and 100 degrees, exactly the temperature range of a cooling kettle. When water boils at 100 degrees, the kettle and the hot water become a thermal reservoir that can sustain a temperature gradient for about 45 minutes. As the water cools exponentially from 100 to 60 degrees, The temperature difference between the kettle base and ambient air drops from 75 to 35 degrees. This cooling follows Newton's law of cooling, giving us a predictable and continuous thermal gradient. Studies on cooked surface heat show that temperature difference between 40 degrees and 65 yield optimal thermoelectric performance. At the start, with different temperature 75 degree, a single thermoelectric module can produce 400 to 600 milliwatts. By the end, at different temperature 35 degree, it still produces 100 to 150 milliwatts. This is enough to power low power smart kitchen device like temperature sensors and timer display, which needs only 50 to 150 milliwatts. Thermoelectric generator typically output only 100 to 500 millivolt, far too low for most electronics. Specialized power management IC solve this. The LTC3108 can start operating at input as low as 20 millivolt and provide selectable output of 2.3, 3.3, 4.5, or 5 volt. This chip uses cascaded boost converters and synchronous rectification to achieve over 80% conversion efficiency even at ultra-low input voltage. They also feature automatic polarity matching, since the TEG's output polarity depends on the direction of the temperature gradient, and include MPPT controller to optimize power extraction. For energy storage, we use a supercapacitor array instead of batteries. Supercapacitors have high power density, low internal resistance, and extremely fast charge-discharge capability. They can endure hundreds of thousands of cycles, making them more resilient for repeat energy harvesting application. Their main role is smooth the intermittent TEG output and provide a temporary power bridge to the wireless transmitter. Thermoelectric generator typically output only 100 to 500 millivolt, far too low for most electronics. Specialized power management IC solve this. The LTC3108 can start operating at input as low as 20 millivolt and provide selectable output of 2.3, 3.3, 4.5, or 5 volt. This chip uses cascaded boost converters and synchronous rectification to achieve over 80% conversion efficiency even at ultra-low input voltage. They also feature automatic polarity matching, since the TEG's output polarity depends on the direction of the temperature gradient, and include MPPT controller to optimize power extraction. For energy storage, we use a supercapacitor array instead of batteries. Supercapacitors have high power density, low internal resistance, and extremely fast charge-discharge capability. They can endure hundreds of thousands of cycles, making them more resilient for repeat energy harvesting application. Their main role is smooth the intermittent TEG output and provide a temporary power bridge to the wireless transmitter.
Assalamualaikum, my name is Muhammad Izzuddin bin Ayub, S72218. Today I will present about 3.0. This slide presents the overall configuration of the proposed hybrid thermoelectric generator and wireless power transfer system. The system utilizes waste heat from a domestic electric kettle as the primary energy source. After water reaches boiling temperature, the kettle reaches a large amount of the thermal energy while cooling from approximately 100 degrees Celsius to 16 degrees Celsius. A BI2TE3 thermoelectric generator is placed at the thermal interface between the kettle and the base station. Due to the temperature difference between the hot kettle surface and ambient air, electrical energy is generated through the Seebeck effect. The generated voltage is the boosted using an ultra-low voltage boost converter such as the LTC3108. The harvested energy is stored in a supercapacitor before being supplied to the wireless power transfer subsystem. Finally, the transmitter coil wireless transfer energy to a nearby receiving device, enabling battery-free operation of low-power smart kitchen application. This slide illustrates the complete energy flow of the proposed system. The process begins with the hot kettle acting as the thermal energy source. The thermoelectric generator converts the temperature difference into a low DC voltage. Because the generator voltage is relatively small, a boost converter increases the voltage to a practical level. The energy is stored inside a supercapacitor to ensure stable operation even when the temperature gradually decreases. Next, a high-frequency oscillator converts the stored DC power into AC power. This AC signal excites the transmitter coil and creates a time-varying magnetic field. Through resonant inductive coupling, energy is transferred wireless across an air gap of approximately 1 to 3 cm. The receiver coil captures the magnetic energy and the receiver converts it back into DC power before supplying into the smart display device. Next, this slide presents the simplified electrical circuit of the proposed hybrid TEG WPT system. The thermoelectric generator produces a low-level DC voltage from the temperature gradient. The EDI3533 converter boosts the voltage and charges the supercapacitor bank. The stored energy is supplied to a Class E oscillator that generates a high-frequency AC signal required for wireless power transfer. The transmitter and receiver coil are tuned to the same resonant frequency to maximize power transfer efficiency. After reception, the AC signal is rectified and regulated to produce a stable DC output. The key innovation of this project is that the wireless transmitter is powered by harvested waste heat rather than a conventional electrical power source. Therefore, the proposed design combines thermoelectric energy harvesting, a wireless power transfer into a single self-powered system for future smart kitchen application. Thank you.
For case study 1, we review a study conducted by Dean et al. 2017, which investigates thermoelectric energy harvesting from a demonstrate hot water system. The objective of the study was to recover wasted heat from a natural gas water heater and convert it into useful electrical energy using thermoelectric generator or TEGs. The system operates with hot site temperature ranging from 50 to 100 degrees Celsius and a cold site temperature of approximately 19.5 degrees Celsius. The experiment's results show that the system was able to generate between 3.9 watts and 42.4 watts of electrical power, with a conversion efficiency ranging from 0.37% to 1.03%. This study is highly relevant to our proposed smart kitchen heater because both systems unite a temperature difference between a hot surface and the surrounding environment to generate electricity. The findings demonstrate that domestic wasted heat can be efficiently harvested and converted into useful electrical energy. In our proposal design, this harvested energy can be conditioned and transferred wireless through wireless power transfer modules to power an external monitoring device. Therefore, this case study supports the technical feasibility of our proposal hybrid thermoelectric energy harvesting and wireless power transfer system. Thank you.
Next, I will present case study 2, which focuses on waste heat generation from a domestic kettle for wireless power transfer application in a smart kitchen. In many households, a large amount of thermal energy remains in an electric kettle after the water has been boiled. Normally, this heat is simply released into the surrounding environment and it's not utilized. Therefore, this project proposes a self-powered wireless power transfer system that can harvest this waste heat using a thermoelectric generator. The harvested energy is then converted into electrical energy and used to power low-power electronic devices wirelessly. In this case study, a domestic electric kettle containing hot water at approximately 100 degrees Celsius is placed on a specifically designed base station. As the kettle gradually cools, a temperature difference is created between the hot kettle surface and the surrounding air. The TEG used this temperature difference to generate electrical energy through the seebeck effect. The generated energy is then transferred wirelessly to a nearby low-power devices such as a smart coffee mug temperature monitor, a kitchen timer display, or a wireless temperature sensor. This demonstrates how waste heat can be converted into useful electrical energy instead of being lost to the environment. The waste heat from the kettle is absorbed by the thermoelectric generator. Due to the temperature difference between the hot side and the cold side of the TEG, a voltage is generated through the seebeck effect. However, the voltage produced by the TEG is relatively low. Therefore, a DC-DC boost converter is used to increase the voltage to a usable level. The generated energy is then stored in a supercapacitor to ensure a stable power supply. Next, the stored DC power is converted into high-frequency AC power using an inverter circuit. This AC power is supplied to the transmitter coil, which generates a changing magnetic field. Through magnetic coupling, energy is transferred wirelessly across an air gap of approximately 1 to 3 cm to the receiver coil. The receiver coil captures the energy and delivers power to the connected load. The expected result of this study is to prove that waste heat from a domestic kettle can be successfully converted into electrical energy and used to operate low-power wireless device. In addition, this system improves energy efficiency by utilizing heat that would otherwise be wasted. It also promotes sustainability and demonstrates the potential for developing self-powered smart kitchen appliances in the future.
Assalamualaikum, this is my part for mathematical modeling. First, we calculate the temperature difference across the TEG model using delta T equal T hot minus T cold. The hot side is attached to the kettle surface at approximately 19 Celsius degree, while the cold side is exposed to ambient air at 25 Celsius degree. Therefore, the temperature difference is 65 kilo. Why use this formula? Because TEG only works when there is a temperature difference between the hot side and cold side. A larger temperature difference produces more electrical energy. Okay, for the formula 2, why use the next formula? Next, the seebeck equation is used to determine the voltage generated by the TEG using a seebeck coefficient of 2020 microvolt and 15 thermocouple pairs. The generated voltage is approximately 0.715 volt. Okay, why did you choose 19 Celsius and 25 Celsius? 19 Celsius represent the kettle surface temperature after boiling, while 25 Celsius represent the ambient room temperature. This value provide a realistic operating condition for the proposed system. Okay. For the last, the mathematical modeling show that waste heat from the kettle can generate approximately 0.715 volt and 51 millivolt, demonstrating the feasibility of the proposed hybrid TEG wireless system. Wireless power transfer system. Thank you.
Thank you. In conclusion, we successfully designed a self-powered wireless power transfer system that uses waste heat as its energy source. By combining a thermoelectric generator, power management circuit, and resonant wireless power transfer, the system can generate and deliver enough power for low power devices such as display, timers, and sensor. This project proves that waste heat can be converted into useful electrical energy, reducing dependence on external power source and supporting sustainable energy use. In the future, a physical prototype can be developed to validate the design and expand its applications. That's all from our group. Thank you.